You hear the number, and it sounds absolute: 299,792,458 meters per second. That is light speed, about 299,792 kilometers per second, about 186,282 miles per second, the hard speed limit built into space-time. It is the fastest anything can move through space, and that makes people think one thing immediately. If you could move that fast, then distance would stop mattering. That idea sounds reasonable, and it is completely wrong once you compare that speed to actual space. But before we continue, please subscribe to the channel to give your support. Let's continue. Light is extremely fast. In 1 second, it can go around Earth about 7.5 times. That is not slow. That is not even remotely slow. The problem is that the universe is so large that even this speed stops feeling like freedom and starts feeling like delay. That is the first thing you have to lock in. The issue is not that light is weak. The issue is that space is enormous on a level your brain does not naturally handle. So start with the moon, because even the moon is enough to begin breaking your intuition. The moon looks close. It feels local. It feels like part of Earth's environment. But it is about 390,000 kilometers away, about 239,000 miles. That means moonlight takes around 1.3 seconds to reach you. So when you look at the moon, you are not seeing it as it is now. You are seeing it as it was more than a second ago. That does not sound dramatic, but it matters, because it means even in the nearest major object in space, reality is already delayed. Then go to the sun. The sun is 1 astronomical unit away from Earth, about 150 million kilometers, about 93 million miles. Light from the sun takes about 8 minutes 20 seconds to get here. So daylight is not live. The sun you see is the sun from more than 8 minutes ago. If something happened there, Earth would not know immediately. Physics already inserts waiting time into your relationship with the nearest star, and that is still the easy version of distance. So ask the next question. If light already takes seconds and minutes in the inner solar system, what happens when you move outward and stop pretending the planets are all packed close together? The answer is that light stops feeling magical and starts feeling like infrastructure. Neptune is so far away that light from Neptune takes about 4 hours to reach Earth. Pluto is far enough from the sun that sunlight takes about 5.5 hours to reach it. Pluto's average distance from the sun is about 5.9 billion kilometers, about 3.7 billion miles. Those are still solar system numbers, not interstellar numbers. And already the idea of one shared present is starting to break apart. That matters more than people realize. A signal, a warning, a command, a mistake. None of it moves instantly. Everything arrives late. If something happens out there, you find out later. If you send something out there, it gets there later. Light speed is incredible, but the solar system is already large enough to turn that incredible speed into lag. And most people still underestimate the solar system because they stop at the planets. The real solar system does not end neatly with Neptune or Pluto. Far beyond the planets, NASA places the Oort cloud somewhere between about 5,000 and 100,000 astronomical units from the Sun. That means the Sun's gravitational reach may extend to roughly 1.6 light-years at the far end. That is a serious number because it means your own star system reaches into distances that are already measured in light-years. That is where the clean textbook picture falls apart. A star system is not just a lamp with a few planets around it. It is a huge region with inner zones, outer zones, and deep outskirts. So before you ever talk about another star, your own sun is already forcing you to deal with scales that are much larger than people casually assume. And once that lands, another problem shows up immediately. A light-speed ship could cross part of that region quickly by cosmic standards, but not because the region is small. It would only feel quick because light speed is the absolute maximum. Real spacecraft are nowhere near that fast. A probe moving at the speeds we actually build would need centuries just to reach the inner edge of the Oort cloud, and much longer to move beyond it. So even before you aim at another star, one fact is already clear. We have barely reached the edge of our own system. That is why the opening idea of this video has to be more precise than just saying space is big. That phrase is too weak. The real point is that light speed only feels unlimited when you think on human scales. The moment you switch to astronomical scales, the same speed becomes finite, measurable, and often frustratingly slow. Look at the progression. The Moon, about 1.3 seconds away at light speed. The Sun, about 8 minutes 20 seconds. Neptune, about 4 hours. Pluto, sunlight in about 5.5 hours. The outer Oort cloud, out to around 1.6 light years. You have not left one star system, and already distance is teaching you the same lesson again and again. Fast is not the same thing as enough, and that is the important shift. Most people hear light speed and think access. Real cosmology says light speed often means delay, even locally. It means the universe is visible but not immediate. It means information moves as fast as reality allows, and reality still does not line up all at once. That is the first crack in the whole dream, that reaching light speed would somehow make the cosmos feel small. Because if one star system is already large enough to make the fastest thing in nature feel limited, then the next step gets much worse. Not the edge of the solar system, not the Oort cloud, but actual human spacecraft. The fastest machines we have ever built sound fast on Earth, but against cosmic distance, they are barely moving at all. Your fastest machines sound impressive until you compare them to the thing you are actually trying to beat. Start with the best case, the most flattering case, the machine we are most proud of. NASA's Parker Solar Probe is the fastest human-made object ever built. At closest approach to the Sun, it reaches about 700,000 kilometers per hour, about 430,000 miles per hour. NASA even says that is fast enough to go from Philadelphia to Washington in about 1 second. By any normal standard, that speed is extreme. It destroys car speed, aircraft speed, even anything your body can naturally picture. But the moment physics enters the room, the mood changes. Light moves at about 1.08 billion kilometers per hour, about 671 million miles per hour. So Parker, the fastest thing humanity has ever built, is only around 0.065% of light speed. Not 6%, not even 1%, far less than that. That means our greatest speed achievement is not close to light speed in any serious sense. It is not almost there. It is not even in the same category. That is the first hard correction this section has to make. People hear a number like 430,000 miles per hour, and their instincts immediately upgrade it into something futuristic. And on Earth, that reaction makes sense. On Earth, that speed is absurd. In the solar system, it is still slow. Against interstellar distance, it is barely the beginning of a real conversation. The number sounds huge, only because your everyday frame of reference is tiny. Then move to Voyager 1, because Voyager is where human pride and cosmic scale really collide. Voyager 1 is moving at about 17 kilometers per second, around 38,000 miles per hour, and NASA describes it as the most distant human-made object ever created. That title is real. It is the farthest artifact our species has ever sent into space. That sounds like the edge of the stars. It sounds almost mythic, but the speed itself tells a much less flattering story. By aircraft standards, 38,000 miles per hour is incredible. By interstellar standards, it is weak. NASA has explained for a long time that at roughly this pace, it would take at least 40,000 years before either Voyager spacecraft even came near another star, and even then, not by arriving cleanly at a destination, not by entering orbit around a world, just by passing within about 1 light year of a star. That is not practical interstellar travel. That is a long drift through deep time, and that comparison is not optional, because this is exactly where people fool themselves. A racehorse can run maybe a few dozen miles per hour. A highway car might do 60 or 80 miles per hour. A jetliner cruises around 500 or 600 miles per hour. Voyager moves around 38,000 miles per hour. Parker can hit 430,000 miles per hour. Those jumps feel enormous. And they are enormous if you stay inside human experience. But light is doing 186,282 miles every single second. Not per hour, per second. That one detail destroys the emotional illusion. The gap between a horse and a jet is small compared with the gap between our probes and light. The important number is not whether a spacecraft sounds fast in a sentence. The important number is how far below light speed it still lives. That is why casual talk about going to the stars usually skips the one thing that matters most, the ratio. Parker is more than 1,500 times slower than light. Voyager is far slower than that. So when someone talks as if current or near-current propulsion puts us at the doorstep of interstellar travel, they are mixing up two completely different scales. They are taking a machine that is impressive in engineering terms and pretending that means it is useful on cosmic terms. Those are not the same thing. And then the Oort cloud makes the whole problem even less forgiving. People like to talk about the nearest star, but we are not even done with the outskirts of our own system. NASA's Oort cloud material puts this in very direct terms. Voyager 1, at its current speed, would need about 300 years just to reach the inner edge of the Oort cloud, and maybe 30,000 years to get beyond the outer edge. That is still inside the Sun's extended frontier. So if one of our best-known deep space probes needs centuries to reach the inner edge of the outermost region of one star system, and tens of thousands of years to move clear of it, then current interstellar travel is not just difficult, it is functionally non-existent. That is the correction people usually resist. We are not a species standing at the edge of the stars. We are a species that has barely reached the edge of its own front yard. Voyager feels legendary because space is so large that even a very slow outward drift can still carry symbolic weight. But symbolism is not propulsion. Distance travelled is not the same as speed relative to the challenge ahead. And the challenge ahead is brutal. So no, you do not get to say, we are fast enough for now. Cosmology does not care about for now. It cares about ratios, travel times, and what the numbers actually mean when distance gets astronomical. Parker Solar Probe is the fastest thing you have ever built, and it is still nowhere near relativistic flight. Voyager 1 is the farthest thing you have ever sent, and it is still nowhere near another star in any useful sense. That is why this part of the story matters so much. Before the universe humiliates your dream with the distance to Proxima Centauri, before relativity, before galaxy-scale travel, your own machines already tell you the truth. Human engineering sounds powerful until it is measured against space, and then it starts to look almost stationary. And that raises the next problem, because once you accept that our best machines are basically standing still by interstellar standards, the nearest star stops sounding nearby too. The word nearest starts sounding misleading, and that is where the next section gets much worse. The nearest star already breaks the dream, and that is a serious problem, because the nearest star is supposed to be the easy one. People hear the phrase nearest star, and their brain automatically translates that into something like close enough to matter. But in astronomy, nearest does not mean nearby. It means least far in a set where every option is extreme. Proxima Centauri, the closest star to the Sun, is about 4.25 light-years away, roughly 40 trillion kilometers, roughly 25 trillion miles. That is the most forgiving interstellar target you can name, and it is still so far away that light itself needs more than 4 years to get there. So the first honest benchmark for interstellar travel is not a dramatic crossing of the galaxy, not some distant exotic system, not another spiral arm. It is one small red dwarf in our local neighbourhood. And even that already forces you into timescales that can swallow careers, governments, and maybe generations. That is what makes the word nearest so misleading. It sounds like the distance should be manageable. It is not manageable in any normal human sense. It is only less impossible than everything else. And once that lands, the next step gets worse because even giving yourself the best possible speed does not make the trip feel immediate. Say the impossible part out loud, just to expose the scale clearly. If you could travel at light speed, and mass cannot do that, Proxima Centauri would still be 4.2 light-years away. Not hours, not days, not weeks, more than 4 years. That is with the absolute speed limit of reality, with nothing faster possible. So even in the fantasy version, where you get the maximum speed the universe allows, the nearest star still does not become convenient. It becomes barely tolerable. Then drop below that, because real spacecraft do not move anywhere near light speed. At 10% of light speed, the trip becomes more than 42 years, and that is before you even start adding the real problems, accelerating up to that speed, surviving the trip, then slowing down when you get there. At 1% of light speed, it becomes centuries, and this is still the nearest star. This is the softest test case. This is the most generous example the universe gives you. if the easiest interstellar target already turns into a decades-long or centuries-long problem, then the phrase "just go to the stars" starts sounding dishonest. That is the trap. People talk about reaching another star as if it is just a bigger version of crossing an ocean or crossing the solar system. It is not. The distance changes the meaning of the mission itself. To cross the Atlantic, you pack fuel, supplies, and a crew. To cross to another star, you may need to pack far more than that. You may need repair systems, medical systems, food systems, air systems, water recycling, shielding, replacement parts, backups for the backups, and if the mission is crewed, maybe even a stable social structure that can survive for decades. At that point, the ship stops being a vehicle in the ordinary sense. It starts becoming a moving habitat. It has to function as a closed environment, not just an engine with passengers inside it. That changes everything. A long interstellar mission is not just a transportation problem. It is a biological problem, an engineering problem, and a social problem. If the mission lasts long enough, the people who leave may not be the people who arrive. If there are children on board, then the destination is no longer just a destination. It is something one generation promises to another. The word trip starts to break down. It is closer to a self-contained human project moving through space than what people usually mean by travel. And then another problem appears, one that sounds simpler but is emotionally brutal once you state it clearly. Even talking to the nearest star is slow enough to break normal human meaning. A message sent to Proxima Centauri takes about 4.255 years to arrive. If something or someone sends a reply immediately, that reply takes another 4.25 years to get back. That means one full question and answer cycle, with the nearest star takes about 8.5 years. That is not a conversation in the normal sense. That is delayed exchange on a timescale that cuts straight through human life. Ask a question as a student, and maybe you get the reply when you are well into your career. Send new data, and years pass before anyone can react. Send diplomacy, and the answer comes back from a version of the other side that no longer exists in the same moment as you. Even if there were a civilization around Proxima Centauri, light speed would not unite you into one society. It would split you into two separate societies, each working with old information about the other. That is the point most people do not fully sit with. Once the communication loop is measured in years, the phrase in contact becomes technically true and practically weak. You can exchange signals, yes. You can prove something is there, yes. You can even build a long history of communication. But you cannot share a present in any meaningful way. You cannot debate in real time. You cannot respond to crises in real time. Light speed does not erase the separation. It defines it. And this is why one star is enough to teach the whole lesson. You do not need to jump to the edge of the galaxy. You do not need black holes, dark energy, or the observable universe to prove the title of this video. One nearby star is enough. Proxima Centauri is close by cosmic standards, scientifically important, and still far enough to break the idea that light speed would suddenly make the universe feel open. That is the point where the dream really starts to die. Before this, you can still tell yourself that space is just large and human machines are just primitive. But once you focus on the nearest star, the excuse starts to collapse. Even at the absolute speed limit, the trip is still measured in years. At lower fractions of light speed, it becomes generational. Communication becomes emotionally empty compared with what the word contact usually means. A crewed mission becomes something much closer to a moving world than a normal voyage. And once you accept that, the stars stop looking like nearby destinations waiting for better engines. They start looking like isolated systems, separated by years, decades, centuries, and eventually much worse. The galaxy stops feeling like a map of places you can casually reach and starts feeling like a field of separated islands. And then the next part makes this even more uncomfortable. Because there is one thing people always bring up at this point. They say maybe relativity helps. Maybe going fast enough changes the clock. Maybe that solves the problem. It helps in one very specific way, and then creates a different kind of separation. Relativity sounds like the rescue, and in one narrow sense it is, but it does not solve the real problem. At high speeds, time does not behave the way your instincts expect. Moving clocks do not stay in step with clocks that stay behind. That is not theory in the casual sense, and it is not a science fiction trick. It is measured physics. Muons are the clean example. A muon at rest has a mean lifetime of about 2.2 microseconds. That is so short that without relativistic effects, many of the muons created high in Earth's atmosphere should decay long before they get much farther down. But because they are moving so fast, time dilation stretches their lifetime in the frame we measure, and they survive long enough to be detected much farther along. CERN's educational material gives the same basic story, and classic CERN storage ring measurements found relativistic muons with a Lorentz factor of 29.33, living about 64.4 microseconds, matching special relativity to high precision. So this part is not optional. Nature really does it. That is the part that keeps the interstellar dream alive. If you move close enough to light speed, the time measured on your own ship can be much shorter than the time measured by people who stayed back on Earth. So yes, relativity can make a long trip feel shorter to the traveller. That much is real, but this is exactly where people smuggle in a false conclusion. Shorter for the traveller does not mean shorter for everyone. It does not make the outside universe wait less. It does not make Earth's clock speed up to match yours. It means the two timelines separate. The crew may experience a smaller slice of time, while the people back home still wait years, decades, centuries or more. Relativity can reduce personal duration. It cannot turn a distant destination into a nearby one for the rest of the universe. And this is not some remote effect that only matters near black holes or inside particle accelerators. Systems above your head are already using it every day. GPS satellites have to account for relativity because their clocks do not run at the same rate as clocks on Earth. NIST explains that once you combine the main relativistic effects, GPS satellite clocks run about 38 microseconds per day faster than clocks on the ground. That sounds tiny, but if engineers ignored it, the positioning errors would build quickly and the system would stop being useful. So the basic idea here is already built into ordinary technology. Your phone can help you find the nearest coffee shop, because real engineers correct for the fact that time is not universal in the simple everyday sense. Einstein is already part of practical life on one planet. That is why this section matters so much. Relativity is real enough to help the traveller, but not generous enough to fix the larger problem. You can tell a physically valid story where a crew experiences a manageable span of time on a very fast trip, but the outside world is not required to stay synchronized with them. Earth keeps aging. Civilizations keep changing. Languages, cultures, even the map of power back home can shift while the ship's clock stays comparatively modest. A crew could leave one era and arrive to find that the society that launched them is transformed or gone. So relativity does not hand you control over cosmic distance. It hands you a trade. You may keep your own elapsed time lower, but only by giving up alignment with everyone else's timeline. And then the final point closes the door. Relativity is not only the reason time dilation happens, it is also the reason you do not get to push past light speed. NASA's own explanations of high-speed travel are very clear on this. Special relativity says light moves at a constant speed in vacuum, and that speed is impossible to surpass there. As you push a massive object faster and faster, the energy cost keeps climbing. You can get closer and closer to light speed in principle, but for an object with mass, you do not cross it by just adding a bit more power. The same rulebook that gives you the strange benefits near light speed is also the rulebook that keeps the barrier in place. So relativity helps, but only in a very specific and limited way. It can make the trip feel shorter on board. It can make long journeys more survivable for the people doing them. It can change the traveller's clock. What it does not do is restore one shared present between separated places. It does not let mass reach light speed, and it does not make distance disappear for everyone else. That is the correction people usually avoid. Relativity is not a loophole that breaks the speed limit. It is the framework that explains both the weirdness near the limit and the fact that the limit still holds. And once that is clear, the next step gets much worse, because you do not even need the whole universe to make light speed feel insufficient. Your own galaxy can already do it. Your home galaxy is already too big for the dream. And that matters, because once the Milky Way is enough to break the idea, You do not need the rest of the universe to do it. The Milky Way is about 100,000 light-years across. Stop on that number because it changes everything. Even light itself, the fastest thing in reality, would need about 100,000 years to cross your own galaxy from one side to the other. So even if you grant the impossible gift of perfect light speed travel, you still do not get a compact civilization spread neatly across the Milky Way. You get a structure where one side is living 100,000 years out of date relative to the other. That is not one connected world in any normal sense. That is a spread of separated regions sharing an origin, but not sharing a present. That is the first big correction. People hear galaxy and think of a place, like a very large country or a very large map. But a galaxy is not a place in the way your brain wants it to be. It is a timescale problem as much as a distance problem. If even light needs 100,000 years to cross it, then administration, conversation, emergency response, and shared decision-making all start to break down immediately. The issue is not only whether ships can travel. The issue is whether anything spread across that kind of scale can still count as one civilization in a meaningful way. Then make it more personal, because you are not even near the center of this thing. The solar system sits about 26,000 light-years from the galactic center, so the supermassive black hole at the center of the Milky Way, Sagittarius A, is not some central hub you can think of as nearby. It is separated from you by 26,000 years of light travel time. NASA and JPL put Sagittarius A at roughly 4 million times the mass of the Sun, and that sounds important, but its importance does not make it accessible. In astronomy, center sounds useful until you attach the actual travel time to it. Then the word loses most of its practical meaning. That is another place where normal intuition fails. In a city, the center can work like a center because travel and communication are fast enough to connect it to the rest. In a galaxy, the center is just another distant region. Except the distance is measured in tens of thousands of years. So even the most obvious landmark in your home galaxy is already functionally remote on any human timescale. And then there is the part people think should make this feel better: the number of stars. It does not make it better. It makes it worse. The Milky Way contains more than 100 billion stars, and some NASA material puts the broader estimate at roughly 100 to 400 billion. That sounds like opportunity, abundance, and endless destinations. It probably means a huge number of planets too, with NASA long emphasizing that our galaxy likely contains billions of planets. But abundance at this scale is not the same as access. A galaxy full of stars is not automatically a galaxy you can move through in any practical way. All those stars are spread across a disk more than 100,000 light-years wide. So yes, the map is rich. The problem is that the richness is spread across a structure so large that most of it remains separated by extreme delay. That is why this section changes the stakes. Proxima Centauri already showed that one nearby star is hard. The Milky Way shows that even if you solve nearby star travel in some extreme future, the galaxy still does not become one coherent home. It becomes a field of isolated systems. There may be worlds everywhere. There may be habitats, stations, colonies, archives, and descendants of one original civilization spread across huge distances. But they would not be living in one shared moment. They would be separated by years, centuries, and in many cases far longer than that. And even the motion of the sun inside the galaxy reinforces how large the stage really is. NASA says the sun takes about 240 to 250 million years to complete one orbit around the Milky Way, with some NASA pages giving about 230 million years and others about 250 million. The exact figure depends on the model and source, but the point is the same. One galactic year is hundreds of millions of years long. That drags the whole discussion out of human time, and even out of ordinary civilizational time. A nation does not wait for a galactic year. A species may not last for a galactic year. Human civilization as we know it is tiny compared with one orbit of our own star around our own galaxy. That is why the Milky Way alone is enough to break the fantasy of a unified star empire. Even at light speed, the galaxy is too large to govern in real time, too large to talk across in any normal human sense, and too large to hold inside one living present. You could spread through it, maybe. You could leave traces across it, maybe. You could build scattered local civilizations inside parts of it, maybe. But you do not get one synchronized civilization spanning the whole disk. You get separated branches linked by history and split by delay. And that is the darker, more realistic version of what mastering the stars would actually mean. Not one seamless civilization crossing the Milky Way as if it were a map on a screen, but a broken network of distant worlds that can never fully share the same moment. The nearest star already damaged the dream. The galaxy finishes the job. And then the next step gets even worse, because once one galaxy is too large, the next question is obvious. If the Milky Way is already enough to make light speed feel insufficient, what happens when galaxies themselves are only the local neighborhood? Even galaxies are only neighborhoods. And that is where the scale stops feeling like travel and starts feeling like time itself is the real barrier. Andromeda, the nearest large galaxy to the Milky Way, is about 2.5 million light years away. That is not a dramatic way of saying far. That is the literal distance. So even if you could move at light speed, the trip would still take 2.5 million years. That is longer than the entire existence of our species in its current form. Once you go beyond the Milky Way, the word journey starts to break down. You are not talking about a mission in any human sense. You are talking about movement across spans so large that the civilization that launched the mission would almost certainly not exist in the same form by the time anything arrived. And there is another mistake people make here. They treat Andromeda like a point, like one dot on a map that you just have to reach. It is not a point. It is a full galaxy of its own. And NASA has described it as spanning about 260,000 light years across. That means your destination is itself a colossal structure, bigger than the commonly quoted diameter of the Milky Way. So intergalactic travel is not just the problem of crossing the gap between two systems. Your starting point is huge, the empty space between is huge, and the destination is huge. Every part of the problem gets worse at the same time. That is why this section matters so much. Crossing from one galaxy to another is not like moving from one city to another. And it is not even like moving from one star to another. You are dealing with structures so large that even the nearest major neighbour is separated by millions of years at the speed of light. And then when you get there, the thing you arrived at is still another galaxy-scale environment with its own enormous internal distances. Then widen the frame one more step, because the Milky Way is not alone. It lives in the local group, a gravitational neighbourhood with over 50 galaxies. That phrase can sound small and familiar if you are not careful, but it should do the opposite. Group in cosmology does not mean tight and compact the way people use the word in everyday life. It means these galaxies are associated with each other, gravitationally, across distances that are still brutal for travel and communication. So even before you start talking about giant clusters and larger cosmic structures, you are already in a multi-galaxy environment where light speed travel still means massive delay. That is the pattern the universe keeps forcing on you. Every time your imagination scales up, the structure of reality scales up faster. You start with planets and the solar system is bigger than expected. You move to stars, and the nearest one is already a major civilizational problem. You move to galaxies, and your own galaxy is too large to behave like one connected world. Then you look outside it, and the nearest large galaxy is millions of light years away, inside a wider group of dozens of galaxies. At every level, the same correction happens. The map expands faster than your ability to cross it. And then there is one more detail that makes this even harder to simplify. Galaxies are not static. They move, they interact, they merge, and they change over deep time. Hubble observations led NASA to conclude that the Milky Way and Andromeda are on track for a major encounter about 4 billion years from now, although more recent modelling has added uncertainty and suggests the exact outcome is less guaranteed than older headlines implied. The important point for this script is not the fine print of the probability. The important point is that galaxy motion is real, galaxy interaction is real, and the timescale for those changes is measured in billions of years. That changes the emotional meaning of intergalactic ambition. You are not looking at a fixed board with stable pieces. You are looking at a universe where the pieces themselves evolve on timescales far beyond human history. So even if you tried to imagine a civilization spreading between galaxies, you would still be imagining that inside a cosmic setting where the galaxies are moving through their own long-term history. The stage is not stable, and the distances are not just large, they are large inside a system that keeps changing anyway. That is why by the time you get to Andromeda, the problem is no longer really propulsion in the ordinary sense. It is timescale. Inside one galaxy, light speed already fails to create one shared present. Between galaxies, it fails so badly that the whole concept of travel starts to lose its familiar meaning. You are no longer discussing whether a ship can get from here to there. You are discussing whether the words here and there still belong to one connected human story, once the separation reaches millions of years. And that is the key result of this section. Galaxies are not the outer edge of the universe. They are only neighborhoods. The Milky Way is one galaxy. Andromeda is the next large one over. The local group contains more than 50 galaxies. Even this local arrangement is already too spread out for light speed to feel sufficient in any normal sense. So if your hope was that maybe the galaxy is the hard part, and then the wider universe opens up, it is the opposite. The farther out you go, the less travel behaves like travel, and the more it behaves like separation across deep time. And then the next section makes this much worse because so far, all of this has at least assumed the universe is just sitting there while you try to cross it. It is not. The problem gets worse when you realize the universe is not sitting still while you try to cross it. Up to this point, you can still make a hidden assumption without noticing it. You can picture space as a fixed map, with objects sitting on it. And the only real challenge is how fast you can move from one place to another. Modern cosmology breaks that picture. On the largest scales, the universe is not static. Space itself is expanding. That is not speculation. And it is not just a visual analogy people use to explain astronomy. It is a measured feature of the real universe. Hubble's work opened that story, and later measurements refined it. NASA coverage of Hubble-based distance ladder results has given values around the low 70s kilometers per second per megaparsec, while ESA's Planck results give 67.4 kilometers per second per megaparsec from the early universe side. The exact tension between those measurements is its own huge topic. The important point here is simpler. Space is expanding, and the expansion is real enough that different teams can argue about the exact rate because they are measuring an actual thing. That changes the whole setup of the problem. You are not trying to move through a frozen stage. You are trying to move through a universe whose large-scale geometry changes with time. So distance is no longer just a number on a ruler. Some distances are changing, while light and matter are moving through them. The arena itself is not passive. And then the story got worse. For a long time, the expectation was that gravity should gradually slow the expansion down. That would still leave the universe huge, but at least the overall behaviour would feel intuitive. Then observations forced a harder conclusion. NASA's Dark Energy Explainer says that after billions of years, the universe's expansion began speeding up, roughly 9 billion years after the Big Bang. That was one of the biggest shocks in modern cosmology. Instead of the cosmos gradually easing off, the large-scale expansion started accelerating. So if your hope was that enough time plus enough speed would eventually let you cross everything, accelerated expansion is where the universe answers back with a much colder rule. Some things are not just far, they are becoming more unreachable with time. That is the pivot in this video. Before this point, light speed looks like an engineering challenge. Hard, maybe impossible for us, but still clean in principle. After this point, the issue is no longer only engineering. It is geometry and cosmic history. A target can be distant in a universe that stays the same. It is a different kind of problem when the background structure of reality is changing while you are trying to close the gap. And the thing driving that large-scale behavior is not some tiny correction hidden in the equations. It dominates the universe. NASA's summaries put the overall cosmic budget at about 68% dark energy, about 27% dark matter, and only about 5% ordinary matter. That means the familiar stuff. Stars, planets, gas, dust, people, ships, engines, all of it is a small minority component. The main driver of the universe's large-scale fate is something we still do not fully understand. And it is not the stuff you build spacecraft out of. That is a very direct collision between human instinct and cosmology. The part of reality you know best is not the part steering the future behavior of the cosmos. That point matters because it stops this from sounding abstract. The expanding universe is not just a background detail. It tells you that the large-scale future of space is being shaped mainly by components that do not look anything like ordinary matter. The stars and planets you want to visit are real, but they are not the dominant influence on what space-time itself does over cosmic time. And this is not hand-waving. We are not just sitting around with equations and guessing that the universe behaves this way. Large surveys are mapping it directly. The Dark Energy Spectroscopic Instrument, DESI, is designed to chart the expansion history of the universe over the past 11 billion years by measuring the positions and redshifts of millions of galaxies and quasars. Public DSI and Berkeley Lab summaries describe targets in the tens of millions, with the 2025 public release alone containing information on 18.7 million objects, including 13.1 million galaxies and 1.6 million quasars. And the broader project is aimed at a much larger 3D map over time. So when you say the universe is dynamic and we have evidence, that is not rhetorical. We are literally building giant three-dimensional maps of cosmic structure and using them to track how expansion has evolved. That is why the consequence is so severe for the idea that light speed would be enough. In a static universe, light speed would at least be a clean finish line. Hard to reach, but conceptually clean. In an expanding and accelerating universe, it is not a finish line. The arena itself changes while signals and ships move through it. So some distances are not just large in the ordinary sense. They are cosmological distances, tied to the growth of space-time itself. At that point, the dream drops to a different level. You are no longer only asking how fast you can go. You are asking whether the target remains meaningfully reachable at all in a universe whose large-scale behavior is making the separation worse. And then the next section pushes this even farther, because once expansion enters the picture, another idea breaks. People assume the age of the universe should tell them its size in a simple way. It does not. That is where intuition fails even harder. The observable universe is bigger than your instincts can handle. And the reason is not just size. It is the way expansion breaks your normal idea of distance. Start with the number people think should make this simple. The universe is about 13.8 billion years old, with Planck results putting it at roughly that age. A normal first reaction is fine, then the observable radius should be about 13.8 billion light years. That sounds reasonable, and it is wrong. JPL, educational material, gives the radius of the known universe as about 46 billion light years. That mismatch is one of the cleanest places where basic intuition fails. The light has been travelling for 13.8 billion years. Yes, but the space connected to those distant sources has expanded while that light was on the way. So the universe is not just bigger than expected. It is bigger in a way that ordinary geometry does not prepare you for. That is the key correction. Age is not the same thing as present-day radius in an expanding universe. If you treat cosmic distance like a simple ruler problem, you get the wrong answer immediately. And that is exactly why this subject keeps breaking people's mental picture of reality. The number 46 billion light-years is not just a larger version of 13.8 billion. It is evidence that the whole setup is less intuitive than it first sounds. Then there is the next distinction. And this is where a lot of confusion starts. When you say a galaxy's light took 10 billion years or 13 billion years to get here, you are talking about look-back time. That is not automatically the same thing as the galaxy's present-day distance in the expanding universe sense. A very distant object can send light toward us, and while that light is travelling, the separation changes because space itself is expanding. So when people say far, they may be mixing together several different ideas without noticing. Far when the light left is not always the same as far now. Once you understand that, cosmic distance stops looking like one clean number and starts looking like something tied to the history of the universe itself. That is why the largest scales are not just large, they are counterintuitive by construction. Your instincts were built for rooms, roads, mountains, maybe planets if you stretch it. They were not built for an expanding metric space where ancient light can reach you after billions of years, while the present-day separation ends up far larger than your first estimate. So the observable universe does not just exceed common sense, It shows that common sense is local equipment, useful nearby, but unreliable at cosmic scale. The number 46 billion light-years matters because it tells you your native picture of motion and distance is too small to trust here. And telescopes make this even more obvious because telescopes do not turn distance into access. They turn distance into history. NASA's Webb material explains that the most distant galaxies it observes are seen as they were more than 13 billion years ago, with record systems observed less than 300 million years after the Big Bang. That means deep cosmology is not contact with the present-day distant universe. It is evidence from the ancient universe arriving late. The farther out you look, the more you are doing archaeology, not travel. You are gathering old information from a younger cosmos. That is extraordinary for science, but it is not mobility. That point matters for the whole argument of this video. People often confuse seeing with reaching. Webb can see farther back than any previous telescope, but that does not mean the universe is becoming more traversable. It means we are getting better at receiving very old light. Observation is not the same thing as access. Knowledge is not the same thing as arrival. Cosmology is full of that distinction. So this is where the scale of the universe stops being just a big number problem and becomes a deeper limit on what accessible can even mean. A universe about 13.8 billion years old, with an observable radius of about 46 billion light-years, is not just larger than expected. It is larger in a way that forces you to rewrite the whole simple story in your head. You cannot just point at that radius and say, fine, give me enough time. Expansion has already made enough time a more complicated concept. The stage is stranger than the speed limit. That is why even light speed starts looking inadequate. And the next section makes it even harsher, because some parts of the universe are visible to you right now and still forever unreachable, even in principle. This is where the story stops being just big and starts becoming harsh. Because in cosmology, seeing something does not mean you can ever reach it or affect it. There is a real difference between the observable universe and the part of the universe we can still influence starting from now. A modern review on the edges of the universe describes a current affectable sphere with a radius of about 16.5 billion light-years, while the observable universe extends out to about 46.4 billion light-years in comoving distance. The key point is simple. There are regions whose old light can still reach us, but anything we send today, even light itself, will never reach them. They are visible but permanently outside our future causal reach. That is where ordinary intuition fails badly. In normal life, if you can see something, then in principle you assume you can go there, touch it, or at least affect it somehow if you had enough time and better technology. Cosmology says that assumption is false. Some parts of the sky are not just distant, they are already outside the region that our future actions can ever influence. So the map is not merely large, it is divided by causal limits. And this is where the phrase event horizon has to be taken seriously in a broader sense. People usually hear event horizon and think only of black holes, but cosmology has its own version. In an accelerating universe, there is a boundary beyond which events happening now can never be reached by signals we send from here today. That is not because our rockets are weak, and it is not because we have not invented the right engine yet. It is because the large-scale expansion of the universe changes the causal structure itself. Some regions are not waiting for better machines. They are simply beyond future contact. That destroys the lazy version of cosmic optimism. A lot of people assume that anything far away is just a temporary engineering problem. The thought goes like this: maybe not now, maybe not for us, but with enough time and enough technological progress, eventually everything becomes reachable. Cosmological horizons say no. Some regions are being carried into permanent causal isolation by the future expansion of spacetime. This is not a temporary gap that descendants can eventually close. It is a permanent separation built into the structure of the universe. And the reason this feels so strange is that observation still continues. We can still receive old light from places that are no longer in practical causal contact with us. That is why the sky can remain rich while the future shareable universe is smaller. We can observe galaxies beyond the event horizon through light they emitted long ago, even though events happening there now are no longer something we can ever respond to or interact with. So astronomy and travel split apart. Evidence and access are no longer the same thing. That is one of the most important turns in the whole script. Up to this point, you could still tell yourself that light speed would solve enough of the problem to make the universe feel open. Here, that excuse collapses. Even perfect light speed travel would still fail against the causal structure of an accelerating universe. The limit is not only on the ship, it is on the future light cone of your civilization. There are places you can see and still never join, never affect, never make part of one shared future. And once that lands, the next section gets even colder. Because now you have to look at the messenger itself. Light does cross the universe better than anything else. And even light does not arrive fresh. It arrives stretched, weakened, and ancient. Light does better than anything else in the universe. And even light does not arrive fresh. The clearest proof is the cosmic microwave background. NASA's COBE mission measured that background radiation at about 2.725 Kelvin, and the spectrum matched a perfect blackbody so closely that the fit was within about 0.03%. That matters because it tells you this is not some vague glow with an unclear origin. It is relic light from the early universe. It is measured evidence that the universe used to be hotter, denser, and very different from what you see now. But it also tells you something else that fits this video perfectly. The deepest light in the sky is not current information. It is ancient information. The oldest cosmic light reaching you is prehistory, still moving through space long after the state that produced it disappeared. And COBE found something even more important inside that relic light. The cosmic microwave background is not perfectly smooth. COBE detected tiny intrinsic variations in it, fluctuations at about 1 part in 100,000. Those tiny differences matter because they were the seeds of later structure. Galaxies, clusters, and the large-scale pattern of the universe all grew out of those tiny, early irregularities. So when you look at the modern universe and think about destinations, systems, galaxies, and vast structures, you are looking at the grown-up version of tiny, temperature ripples in ancient radiation. That is real observational cosmology, and it makes the point very directly. The universe you want to cross was shaped by processes that were already underway billions of years before your species existed, and the light that tells you that story is only reaching you now as a fossil record. Then add redshift, because this is where light stops looking like a perfect messenger. In an expanding universe, light traveling through space gets stretched. Its wavelength becomes longer. That means it shifts toward the red, and beyond visible red into infrared and other longer wavelengths. NASA's Hubble and Webb material explains this very clearly. Light from distant galaxies does not reach you in the same form it was emitted. The universe changes it on the way. The farther the journey, the greater that stretching can be. So light survives the trip, but it does not cross the cosmos unchanged. That point matters for the whole logic of this video. Even light, the fastest messenger in reality, does not travel through the universe like a clean signal in a perfect wire. Space itself expands while the light is moving. And that expansion edits the message. The information arrives, but it arrives transformed. So if the best messenger in nature does not cross the universe in a clean, untouched state, that should tell you something about what cosmic distance actually does. And that is why telescopes are time machines in only one narrow sense. Webb and Hubble can see deep into the past because light takes time to travel. NASA's Webb explainers say the light from the most distant galaxies Webb has viewed left those galaxies over 13 billion years ago, meaning we see them as they were only a few 100 million years after the Big Bang. Recent Webb results pushed that to galaxies seen as they were about 280 million years after the Big Bang. That is extraordinary science, but it is not present-day contact with those systems. It is controlled delay. The farther out a telescope reaches, the older the news becomes. That is the reframing this section has to force. Astronomy feels like access because it gives you detail. You can map galaxies, measure spectra, study early structure, and reconstruct cosmic history. But detail is not immediacy. The cosmic microwave background, redshift, and deep Webb observations all say the same thing in different ways. Light is not a bridge to now. It is a carrier of old states moving through changing space-time. That is why astronomy is so powerful for knowledge and so weak as evidence for seamless connection. The universe lets you observe its past much more easily than it lets you enter its present. And that leads straight into the next problem, because even if you somehow solve time, distance, and causality on paper, there is still the trip itself. Empty space sounds harmless until you try to cross it at serious speed. Empty space sounds harmless until you try to cross it fast. People talk about interstellar space like it is just nothing, just a blank gap between stars. It is not nothing. NASA educational material says the average particle density in interstellar space is around 1 atom per cubic centimetre, and NASA also reported a local neutral hydrogen density near the termination shock of about 0.127 particles per cubic centimetre. Those numbers are extremely low, but low density is not the same as no density. Across light years, that thin material becomes a real medium. If you move through it slowly, it mostly feels irrelevant. If you try to move through it at a large fraction of light speed, it stops being background and starts becoming a continuous stream of impacts. That is the part people usually skip. A vacuum at human scale feels empty. A vacuum stretched across interstellar distance is still full of particles, dust and radiation, just very spread out. And once your speed gets high enough, even tiny things stop behaving like tiny things. A microscopic grain of dust hitting a craft at relativistic speed is not a minor annoyance. The relative velocity makes the impact energy severe. NASA technical studies of relativistic interstellar probe concepts explicitly treat radiation from motion through the ambient interstellar medium as a major design issue, and they note that intersection with interstellar dust can physically damage spacecraft materials. So shielding is not a side detail. It becomes one of the central problems. Then add radiation, because the medium is not just about dust. NASA's Interstellar Probe Power Study says a fast probe would accumulate radiation dose during a 20-year cruise from both cosmic rays and from its motion through the ambient interstellar medium. In the spacecraft frame, the incoming environment becomes more energetic, not less forgiving. So the faster you go, the more the trip itself starts fighting back. That does not automatically make interstellar travel impossible, but it does make the phrase "just go really fast" sound naive. Speed is not a pure advantage anymore. It also increases hazard. That is why the void is not a neutral gap. It has structure. It has particles. It has dust. It has long exposure times. On slow missions, that mostly means wear and engineering limits. On relativistic missions, it means repeated assault from a medium people casually call empty. So even before you ask whether you can generate the speed, you have to ask whether a ship can survive the trip through what is technically sparse but physically still real. And that is where the clean version of the light speed dream starts falling apart again. On paper, it sounds simple. Distance divided by speed. In reality, medium matters. Impacts matter. Shielding mass matters. And damage builds up over the whole route. The universe does not give you a perfect frictionless corridor between stars. It gives you a thin but hostile medium stretched over enormous distances, and that is enough to become dangerous once your speed gets serious. Distance is not the only enemy. Physics keeps adding more. And then the next problem is even worse, because even if you could survive the trip, you still have to pay for it. The energy bill is where the whole idea starts turning from difficult into brutal. The energy problem is bad enough on its own, even before the galaxy, even before cosmic expansion, even before horizons. You do not just need a better engine, you need an absurd amount of energy. Start with the gap itself. Parker Solar Probe is our speed champion at about 700,000 kilometers per hour, about 430,000 miles per hour. That is extraordinary engineering. But light moves at about 1.08 billion kilometers per hour, about 670 million miles per hour. That is not the kind of difference you close with one more generation of hardware. That is a jump of more than 3 orders of magnitude. So when people picture progress as a smooth line from today's probes to relativistic spacecraft, they are flattening a cliff into a ramp. Then look at what even modest fractions of light speed actually cost. A probe with a mass of 1,000 kilograms and about the mass of a small car, moving at 1/10 of light speed, carries about 4.5 times 10 to the 17 joules of kinetic energy. That is a little over 100 megatons of TNT equivalent. Push that same 1,000 kilogram probe to half the speed of light, and the kinetic energy jumps to about 1.39 times 10 to the 19 joules, which is multiple gigatons of TNT equivalent. At 9/10 of light speed, it rises again to about 1.16 times 10 to the 20 joules. And that is just the idealized kinetic energy of the payload itself, not propulsion losses, not shielding, not onboard systems, not the energy needed to slow down at the destination. That is where the dream starts turning into a nightmare. Because rockets do not just charge you once, they charge you twice. NASA's rocket equation material makes the basic problem clear. To get more speed, you need more propellant. But that extra propellant has mass, and that mass also has to be accelerated, which means you need still more propellant. For ordinary missions, this is already painful. For relativistic missions, it becomes brutal, because the mass problem does not scale in a friendly way. So when someone says we will just build a bigger rocket, they are trying to solve a hard mass problem with optimism. Physics does not care, and this is why real propulsion research has to be talked about honestly. Solar sails are real. NASA's ACS-3 mission is real. Ion propulsion is real, and NASA's Dawn mission used ion engines for years of thrust. Beam-driven sail ideas and fusion ideas are serious areas of study too, but none of that changes the empirical benchmark. Our actual record holders are still Parker and Voyager. Parker is still only a tiny fraction of light speed, and Voyager 1, the farthest human-made object we have, is moving at about 17 kilometers per second, about 38,000 miles per hour. That is why the honest version of the story is not we almost have interstellar travel. The honest version is we have started learning how brutally expensive high-speed travel really is. So the title survives another direct hit. Lightspeed may already be unimaginably hard to approach because the energy bill alone starts getting violent long before you arrive. And then after all that, even if you somehow pay that bill, the universe still does not become easy. It is still too large, too delayed, and too dynamic. So the problem is layered. First, reaching anything close to light speed may be a nightmare. Second, even that nightmare still does not buy you what your instincts promised. And that leads to the next part, because even if propulsion became miraculous, there is still one thing light speed cannot fix. A civilization spread across distance still cannot rule by conversation. Even if your ships became incredible, a civilization spread across distance still could not rule by conversation. You can already see that inside our own solar system. NASA says Mars missions deal with about 4 to 24 minutes of one-way communication delay, depending on where Earth and Mars are in their orbits. That alone kills the fantasy of real-time control. You cannot drive a Mars rover like a remote control toy from Earth. By the time a command arrives, the situation may already be different. That is why Mars systems need autonomy, and why any serious Mars mission has to assume a level of local decision-making. Distance makes central control physically slow, even before you leave the inner solar system. Then go outward to Pluto, because Pluto makes the point even more clearly. During the New Horizons flyby, NASA noted a round-trip signal time of about 9 hours, with one NASA page describing the encounter as requiring a roughly 9-hour round trip for signals between Earth and the spacecraft. Another educational breakdown for the Pluto mission gives about 8 hours, 50 minutes round trip, which means roughly 4 hours, 25 minutes one way under those conditions. So even a simple exchange with a spacecraft near Pluto stops feeling like communication in the normal sense. It starts feeling like slow correspondence. The outer solar system is already too delayed for real-time command. And then there is the Voyager 1. NASA's current Voyager tracker shows one-way light time for Voyager 1 at around a full day, depending on the exact date. That means a command sent from Earth takes about a day to arrive, and confirmation takes about another day to come back. That is with an object that is still in the Sun's broader domain, not at another star, not in another galaxy, not anywhere remotely close to the scales people casually talk about in science fiction. If the most distant artifact we have ever built is already untouchable in real time, then the idea of tight centralized control over interstellar distances is not serious. That is the pattern the universe keeps forcing on you. Delay is not a side issue. Delay changes what kinds of systems can exist. At Mars, you need autonomy. At Pluto, you are already waiting half a day for a simple exchange. At Voyager distance, the timing feels more like letters than commands. So by the time you get to Proxima Centauri, with a 4.25-year one-way light time, or the galactic center at around 26,000 years one-way, the word conversation stops meaning what people think it means. You are no longer talking about communication for command and control. You are talking about messages crossing historical eras. And that means a light-speed civilization would not look like one clean empire. It would look like separated branches of a shared origin. Law would drift, language would drift, identity would drift, culture would drift. By the time messages move between regions, the societies receiving them would already be different from the ones that sent the originals. Shared reality would get thinner as distance increased. Central authority would not just weaken. It would become physically outdated. That is the sociological version of the title. The problem is not only that travel is hard, the problem is that causality itself limits how unified a civilization can remain. The farther you spread, the older everyone's information becomes. So the fantasy of one civilization ruling the stars in any tightly coordinated way collapses very quickly. First into loose federations, then into distant descendants, then into cultures linked more by history than by active exchange. The universe does not just limit movement, it limits how much togetherness distance allows. And then the next section closes the loop from another angle, because none of this is just a temporary engineering limit waiting for a clever trick. Observation has already tested the speed limit itself, again and again. This is not just the fastest speed we have managed so far, it is the speed limit built into the rules themselves. A lot of people still talk as if light speed is just today's record, and tomorrow's genius might get around it. But that is not what modern physics says. The speed of light is part of the structure of relativity, and it has been tested in very different ways, with very different instruments, across very different parts of science. The universe has had many chances to show a crack in that rule. So far it keeps refusing. You can see that clearly with muons. CERN's teaching material gives the muon a mean lifetime of about 2.2 microseconds. That is extremely short. Without relativistic time dilation, many of the muons created high in the atmosphere should decay before they get very far. But they are moving close to light speed, and because of that, their lifetime is stretched in the frame we measure. CERN's classic storage ring measurements found relativistic muons with a Lorentz factor of 29.33 living about 64.4 microseconds, in agreement with special relativity to high precision. That matters because it proves both sides of the same framework at once. Time dilation is real, and the same relativity that gives you that strange behaviour is also the framework that protects light speed as a limit. You do not get to keep the weird part you like and throw away the limit you do not like. Then there is the everyday proof sitting above your head right now. NIST explains that GPS satellites have to account for relativistic effects because their clocks run about 38 microseconds per day, faster than clocks on Earth, once the main effects are combined. That sounds small until you remember what GPS is trying to do. Small timing errors become large position errors very quickly. If engineers ignored relativity, the system would fail. So this is not some remote corner case from particle physics. The same framework that says nothing with mass outruns light is part of the reason your navigation works. The rules are not just theoretical, they are embedded in functioning technology. And then gravitational wave astronomy made the case even stronger. In the event GW170817, gravitational waves and a gamma-ray burst counterpart were observed with a delay of about 1.74 seconds from a source more than 100 million light-years away. LIGO's published analysis used that to constrain the difference between the speed of gravity and the speed of light to between about negative 3 times 10 to the minus 15 and positive 7 times 10 to the minus 16. NASA presentations summarize that result more bluntly, saying the speed of gravity matches the speed of light within about 1 part in 1 quadrillion. That is a very hard result to ignore. Nature had another chance to reveal a shortcut around the speed structure of relativity. And again, it did not. That is why the speed limit is not just famous. It is over-tested. Particle lifetimes, atomic clocks, satellite navigation, gravitational wave observations, these are different tools, different eras, different scales, and they keep landing on the same answer. Light speed is not just a number in a textbook. It is one of the deepest organizing rules we have ever measured in physics. So when you say we can travel at light speed and it still will not be enough, the statement carries two separate blows. First, light speed is probably the real ceiling. Second, even that ceiling is still too low to make the universe feel small. And that sets up the final escalation, because once the speed limit is real, and once even that real limit still fails against cosmic scale, one conclusion starts to become unavoidable. The universe is not built to be crossed. The final answer is that the universe is not built to be crossed. And cosmic history itself already tells you that. The first stars did not appear instantly. NASA says the first stars likely formed as early as about 100 million years after the Big Bang. And other NASA summaries say that over several hundred million years, the first stars collected into the first galaxies. That matters because the universe did not show up fully assembled. It built structure slowly, in stages, over immense spans of time. So every destination you care about, every star, every planet, every galaxy, belongs to a long unfolding history. The cosmos is old, not just in age, but in process. Then there is cosmic noon, the period when star formation really peaked. ESA describes that peak as happening around 2 to 3 billion years after the Big Bang, and says galaxies formed about half of their current stellar mass during that period. ESA also describes it as the era when star formation and galaxy growth entered a much more intense phase. That means the universe is not just a big, static arena. It has eras. It has active periods and quieter periods. We live after major formative chapters have already happened, looking back at the results. So when you talk about traveling through the universe, you are not entering a timeless map. You are entering a place with a deep history, where important windows opened and closed long before you arrived. And then the scale gets even worse, because the part you can observe may be only a fraction of the whole. Planck results are consistent with a universe that is extremely close to spatially flat. ESA's published summaries put the curvature result very close to zero. Flatness does not prove the universe is infinite, but it does support the idea that the total universe may be much larger than the observable patch, and possibly unbounded on the largest scale. So the part you can even see is already beyond simple mastery, and the full reality may extend far beyond that. The map is not just too big, it may be radically bigger than the part you will ever know directly. So what does light speed actually buy you? It buys you the moon in about 1.3 seconds, the sun in about 8 minutes 20 seconds, Pluto scale distances in hours, the nearest star in more than 4 years, the galactic center in about 26,000 years, and a Milky Way crossing in about 100,000 years. It buys you some reach inside the local universe, but not ownership of the cosmos. It buys you survival against certain distances, maybe enough for signals, maybe enough for rare journeys, maybe enough for scattered local civilizations. But it is not enough for immediacy. It is not enough for one shared present. And it is not enough to turn the universe into one connected place. And that is the closing point. You spend your whole life treating light as the thing that gets there first, the thing nothing can outrun, the thing that makes the universe visible. Then cosmology gives you the harder truth. Even the fastest thing in reality is still too slow to turn the universe into one place. Not because light fails, but because the cosmos is larger, older, more dynamic, and more causally fragmented than your intuition was ever built to handle. Light speed is ultimate, and the universe still wins. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.